Okay, good day everybody. We are starting this organic revision, but we have just a one single little very short hour. I don't know how much we would do. I'm gonna go through the full syllabus with this little short hour. I'm just gonna touch everything when I'm going through this part. Then you would get the idea. Wow, this part is I remember. The next part I don't remember. I have to go through this again and again and so on. Four units together makes the organic chemistry. This is again gives us 25 marks. So if you are done with organic chemistry, if you get through all the questions with organic chemistry, then you have everything with you. Okay, I'm just gonna go through this first part. We were talking about these benefits, users, and the next part is why they have this vast variation of organic compounds. That's again you can understand very easily. I'm just gonna go on. This classification is actually the syllabus. The reason I've given all these names for you guys, because then we went on to this nomenclature. During the nomenclature, you should understand what is the groups of these different compounds, just to get that functional groups are like this and that. I've given this part. Now you don't want this, even don't turn these pages. You can just go on. Then we went on with this different formula. There are 5 different formula. So the empirical formula gives a simpler structure. Exact amount gives the molecular formula. Connecting pattern gives the structural formula. Then if you have lone pairs on connecting pattern, that is the Lewis structure. Getting this carbon and hydrogen as lines, if you go with this structure, this is called the bond line structure. That's again very easy. Then we are moving to this homologous series. One single formula, common formula for each homologous series. I'm not going to go through this because in your short note, you have all these parts together. All the homologous series are together. Any group, one atom or couple of atoms together giving particular qualities is the functional group. Nomenclature, general naming. Did I give this to short note? No, I didn't give this to short note. So I want you guys to write this to short note because you have to memorize these again. And also, I have given this kind of a general naming for benzene compounds as well, benzene derivatives. So add that to the short note as well. I want to add this later, but when I was doing this revision, I was having a feeling memorizing these compounds are also not easy, little challenging. And then I'm not going to go through this nomenclature part, just the linear, the long chain, one branch, iso, 2 branches, neo, then primary, secondary, tertiary, 3 R groups tertiary, 2 R groups secondary, 1 R group primary, then the IUPAC nomenclature. So if I go through this IUPAC nomenclature, it takes a lot of time. So I'm not going to go through this one. You guys can go through that. Only thing I want to emphasize is this table. Again, I asked you guys to keep this table somewhere you can see regularly in front of your study table also. So main functional group, the main group and the substituent group. Remember that carboxylic acids and esters never become substituent groups. Those are only main functional group. For other groups, if they are the first priority, number 1 priority, they are acting as the main group, or otherwise they are acting as substituent groups, so that we have 2 different names. This is the priority list. So you have to go through this variation. Okay. Then we did a lot of questions. Even this, when I was doing this one to Colombo students, I was feeling like, do I need to do that many homework, that many questions? Okay, all these questions we did. What you can do is try these questions, get the answers, check your answers with the note. If your answers are correct, you are through with nomenclature, then you have the knowledge. Then the next part is, when they were given the naming, how do you get this structure? So if they were given the name, first thing is to find this, how long the carbon chain. To get this, how long the carbon chain. You have to go with this name. So this is hept, that is 7 carbon. So you are just drawing 7 carbon. Then the last name is the main functional group. Then go one by one and fill these gaps with given these groups. So that's easiest way to get these structures. Isomerism is extremely important. Extremely important. If you still feel like isomerism is harder, go through the note very nicely. Isomerism, one single structural formula, but different compounds. If you can see these difference obviously to naked eye, that is a structural, not the naked eye, like you looking at the structure. Looking at the structure, if you see any difference, that is structural isomerism. If spatial arrangement is different, that is stereoisomerism. Structural isomerism comes to the chain, that is the chain isomerism. Same functional group, but in different position, positional isomerism. If there are two different functional groups, but same formula, that is the functional group isomerism. Spatial arrangement, if they are mirror images of each other, non-superimposable mirror images, those are enantiomers. If they are non-mirror images, one is not like the mirror image of the other one, those are diastereomers. Through the diastereomerism, geometric, cis, trans, and easy, one carbon, the other carbon, C1 and CX and CY. CX supposed to have two different groups. CY supposed to have two different groups. Okay. So cis trans. If see, I have taken these two same. So this is going to cis trans. Let's say all these four groups are different. Let's say I have a star here. All four groups are 1, 2, 3, 4. All four groups are different. Then what is isomerism? Easy isomerism. What is optical isomerism? Enantiomerism. These compounds, they are non-superimposable mirror images, and that comes through one carbon is joined into four different groups. One carbon is joined into four different groups. Those are called chirocarbon. Only compounds with chirocarbon are having optical isomerism. That's all. I'm not going to explain each of these separately. Then moving to here. Students are supposed to come to collect organic Sinhala medium students. They can wait. The class is on Friday. They will keep calling. They need organic theory. Be inspired like them. Couple of these students are doing so well. They don't come to the class not doing any question. You guys know that me, Asha, they are not coming to class, not doing anything. They do everything before coming to the class. Okay, so different kinds of types of reactions. Substitution, one group or one atom gets away, another group or another atom joins. Addition, you add groups so that you are breaking triple or double bonds, going to double bonds or single bonds. Even CO, it's not always only CC. CO is also possible to break. Anyway, you are adding small group. Elimination, you are removing groups. So by removing groups, you are making double bonds or triple bonds. Last one is redox. You could see the oxidation numbers are changing. Whenever you are making a reaction, there are two different kinds of breaking of bonds, homolytic and heterolytic. Homo mean both these atoms are claiming electrons the same way, so that each are getting same number of electrons. Bond breaking energy is now storing in these atoms, so these atoms have higher energy, normal atoms, but with higher energy, so we call them free radicals. But if the electronegativity difference is high, one is claiming more electrons, A electronegativity high. So this gets both bond electrons, getting the negative, and this is the positive. Negative are called carbanion, positive are called carbocation. Those are the two species coming from these. Anyway, inside the mixture, there are two different species. Active species, those are electrophiles and nucleophiles. Electrophiles, less electrons. So they attract negative charges. Nucleophiles, more electrons, they attract positive charges or nucleus. Okay, when they break bonds, they are making carbanion, carbocation, and free radical. Carbocation has plus charge. Simplest one is alkyl. I'll go together. Alkyl means directly plus charge is on carbon. Plus charge is on carbon. stability comes to this inductive effect. The ability of pushing on electrons to neighboring atom is inductive effect. When you are providing more and more negative electrons, plus charge is controlling, plus charge is weakening. So its activity is weakening, it is getting more stable. Inductive effect high, carbocation stability is high. Then the second one is the allyl carbocation, mean you have double bonded carbon. To that double bonded carbon, C plus is attached. But you have the importance here, this C plus can be localized within the double bond. So that this is making resonance structures, which is called the resonance stability. So allyl carbocations are so that more stable comparing to this alkyl carbocation. Allyl are more stable because it is making resonance. But benzyl carbocations is benzene ring. C plus is joining to benzene ring. Those are very stable, more stable because this plus charge can delocalize within the benzene ring, and see, allyl carbocation is making 2 resonance. So only in the middle you have 3 resonance. If you go with this one, there are 4 resonance. So in that way, benzyl carbocation is very, very stable. Carbocation stability, we did questions always, and this one I also given for the short note as well. Whenever you have something from the note, if it is in the short note, just write there, refer short note. When you are reading the short note continuously, you get the knowledge, then the time you are spending for normal theory note become very, very less. Anions, so you have this negative charge on carbon, free radicals that you have one single electron, those are called free radicals coming through homolytic cleavage. So we are done colorimeter. Moving to how much time? 10 minutes, I guess. Are you guys okay like this? I know I'm going a little faster. Concentrate really, really well. This is not a theory class. I'm just refreshing your knowledge. And even, you know, just some of these tuition people are saying they do that. They really do that. But they are saying no point of going to revision classes. What's the meaning of revision classes? Revision mean this kind of revision class is really effective. Correctly targeting to your brain to give the advantage or this push that you have to go through the note. But doing the revision, exactly the same thing. Again, you are doing all these questions in a revision class, writing the note in a revision class. What is the point of that? Just wasting time. It's like you are going to 2 different theory classes. I would never recommend that revision, and I would never do that revision. Yeah, my master of my Canada master instructor. Okay, this beautiful life is just ahead of you. You guys can go there. I know that really. We after 15 years, not 10 years. 10 years mean if you are going to this medicine or engineering faculties, then you have like, especially the medicine 5 years, then here you have to do this intern, and then another 2 years, I guess, to do this part 1 and part 2, then only you can go abroad. So maybe 10 plus years. Okay, anyway. Okay, so the rest of the part, I'm not going to go that faster, but still I know this is very, very easy because we have the knowledge and we done everything very nicely. So alkanes are saturated. It simply means there are no single, double or triple bonds. Physical properties, only thing you want to remember is they are non-polar. So London forces, molar mass and contact surface area. They are targeting that part to get answers. Then only one single chemical reaction, that is the halogenation. So the very first step is by the halogenation, you can join whatever the number of halogens you supposed to join. It's totally up to you. In initial step, there are 3 different steps: initiation, propagation, and termination. By the initiation, Pacific is coming, I guess. Who cares? You are breaking this halogen bond. That's because this CH bond is stronger. This one is stronger. Even in the presence of sunlight, you cannot break this. But you can break this by breaking. You are making high energy halogen. So that halogen is now attacking onto another CH. So attacking onto this, joining this, making HCl. Now this is become free radical. Going on and on and on until you have no more CH bonds if you give enough chlorine to do that. Anyway, that is a propagation. For the termination, there are supposed to be a method to remove free radicals. That's how you're going to go to termination with the given species there. Here you can go with any of these free radicals. Any of these free radicals. Once the free radical is not there, you can go through the reaction continuously. Then formation of alkanes. Both these are carbonyl compounds going with the Clemmensen, and both these are unsaturated. Any of these hydrogen and catalysts, you can go for alkanes. And the Greenard at that time, it was really hard for you to introduce Greenard. Now you guys know that this bond breaks from here. R prime gets a hydrogen from this one to make this alkane. Questions I've given just to make sure you are in the right path. Okay. Now we are done with the alkane box. What is the next step? You are going through the spider diagram and just memorize the alkane box. Okay, that's how you're going to study this one when you are doing this at home. See, if you want, you can write that. Here I have written that because sometimes I forget to explain this for students. Discuss box with inorganic short, not the short, not in organic spider diagram. Okay, just right after that alkane box, alkane topic done, you can write that box. I'm not going to explain that now. You're going to do that. Okay, now I'm going to alkene double bonds, same intermolecular interactions. Chemical reactivity is the most important. Okay, you have the double bond. So the high electron density, double bond mean high electron density. So who comes to attack? Who like electrons? Who like electrons? Electrophiles are coming. Then they have to break these bonds. Then addition, they have to join here. So the characteristic reaction type is electrophilic addition. Other than that, oxidation and reduction is also possible. Very first mechanism. So here, bromine is normally non-polar. So when they are in their own solution, freely they are non-polar, but when they are getting closer to this double bond pushes these electrons away from its own bond. So this side gets plus, this side gets minus, getting the benefit of having this plus. This double bond is tagging onto this bromine. Then this one breaks from here. So bromine joins, this one gets away as Br minus, and this carbon plus is unstable. So you have this bromine has lone pairs and trying to donate, but then what happened? This gets a plus charge, that's again really unstable. So it is trying to drag electrons from this direction. So this is come and join back onto this carbon. Dibromo. For conversions, you only need this. This is the hardest. So the next one is to understand HBr. Then hydrogen is already having this, I lost the annotation. Hydrogen is already having this polarization, hydrogen plus and Br minus. So when the hydrogen plus is getting closer to this C double bond C, that C double bond C is providing this electron onto hydrogen and joins with hydrogen. So HBr bond breaks. I don't want to waste a second even. Otherwise, time wouldn't be enough. So this HBr bond breaks, hydrogen joins, then you have the C plus, Br minus come and join there. So you make an HBr. That is very easy to understand. The problem comes with, so if you have asymmetric double bond, then how do you know to which carbon this bromine is joining? That depends on this, where this plus charge is on. That depends on the stability of carbocations. It is going through more stable carbocation. That is the method. But always, how do you find the stability of carbocation? So it's frustrating. So understanding that. So please empathize, you guys, I guess. Markovnikov. So Markovnikov introduced this rule. Hydrogen goes to where hydrogen is high. Maybe I'm speaking a little faster. I want you guys to go home and go through this recording again. Then you would get this better knowledge, okay? I'm going a little faster. One single thing is we have just a 45 minutes. Second thing is we went through very nicely with the theory. Okay, couple of examples we can go with that. Then the third one is concastuous sulfur. With concastuous sulfur, what is it? With concastuous sulfur, we have only this. We don't have water in the medium. So this dissociation is not that good still. So then this double bond is giving its electrons away, so that this hetero bond can polarize towards oxygen, so that this hydrogen is joining here. This HSO4 minus is getting away, but you don't have any other nucleophile. So this minus again coming back and join here. And exists like this until you add water. Once you add water, this total part is getting away. Water coming from OH joins here. And H2SO4 regenerating, that acting as a catalyst. Anyway, you are just making this alcohol. That's again going through this Marconi form. Del H2SO4 condition is different. In del H2SO4 medium, that you have H plus OH minus coming from the medium. That OH minus reacting with this can make, this H2O reacting with this H plus can make H3O plus. So water has the ability to polarize this H2SO4 to get this H plus away. So the medium has this free H plus. That H plus is joining with C double bond C. You are coming to this position. Now we have both this HSO4 minus and its H2O. H2O is acting as a better nucleophile and attacking onto this carbon. But then oxygen gets a plus charge. Break from here, you are making the alcohol. And H2SO4 is regenerating. Antimarconic of mean, if you have alkyl peroxide or hydrogen peroxide, hydrogen goes to where hydrogen is less. You need that for conversions as well. This again, you guys had little issues even at that time. Oxidizing agents, acidic and basic. In acidic medium, this one breaks. That's why I have given this one in our short note. I have given this as a chain shortening method. During the chain shortening, you can use this alkene oxidation. So this one breaks. Sometimes you are doing conversions, one's not breaking, you are making whatever this silly compound by adding potassium permanganate to double bonds. Don't do that. Double bonds supposed to be break. It is breaking as long as it has CH. Okay, if you break from here, this doesn't have any CH, so it is just existing as it is. This is converted into HCOH. C2CH. So convert into this. That again has one CH. Then it is converted into this. So going on and on and on up to breaking all CH bonds. So if you have CH2, it is giving CO2. Remember that they can make like they are not giving directly CO2, but they are giving this one and potassium permanganate. Then you have to make CO2. Okay, these are the hints of me. Guessings, I mean. Okay, if you have this condition, so they are making CH2, but converted to COOH. Now there are no more CH to break. And if you have different two compounds, so it is giving two different carboxylic acids. Concentrate well because you missed that. Alkaline medium, it's very easy. Double bond breaks, two OH groups are joining. That is called the Bayer's reagent. Reduction again easier, going to make alkanes with any of these catalysts with hydrogen. Then formation of alkene. To make the alkene, always you're supposed to have either one halogen or one hydroxide. Sorry, one hydroxide or one halogen. Hydroxyl group, concatenation of 170. Halogen, alcoholic potassium hydroxide or sodium hydroxide. And with these alkynes, Lindner catalyst and H2. Partially reduce triple bond to double bond. Okay, see how easy. Now we are done with alkene. So go to the second box, alkene box, and analyze all these reactions I've given there. Make sure now it is in your brain. Don't always, okay. The other thing I want to tell you guys is not like inorganic chemistry. I don't want you guys, when you are doing organic chemistry, going back and forth and get knowledge from book. You have to first finish the theory note. Then you are doing questions. Don't go back and forth checking your, it's okay if you can't memorize anything, it's okay to go on, but not like inorganic. Whenever, remember the way we started inorganic, I said as a open book, just get everything from the note. Don't do this for organic. So you're not improving your memory. Just you can use the short note and this spider diagram, but later, just don't even look at the spider diagram. Because you cannot, whatever you cannot bring for the exam, don't trust them. Trust only your brain. Okay. That's the way for organic. Okay, alkynes, they have triple bond. Again, same intermolecular interactions. I'm going with reactions. So alkynes has triple bond. Again, in electron density is high, so it's supposed to have going through with this electrophilic addition, but the reaction rate is less because triple bond energy is high And once you break a one bond, this is making triple bond making vinyl carbocation, while double bond making allyl carbocation. Vinyl carbocation is very unstable, so they don't like that. They do reactions, electrophilic additions, but less reactive comparing to alkenes. So with bromine, they go with 4 bromine. With HBr, 2 hydrogen and 2 bromine. Remember, you have to follow the Markovnikov rule. Hydration, by the hydration, they are making this enol compound. This is a middle compound, unstable. Finally, you are making this carbonyl compounds. Oxidation is in syllabus, but products are out of syllabus. Just memorize, it can go to oxidation. Reduction is, there are 2 different reduction, partial and complete. Partial reduction, same hydrogen and catalyst. See, same hydrogen and catalyst. But here it is going from triple bond to single bond. To control, not to break both pi bonds, you are adding quinoline. To absorb quinoline, you are adding barium sulfate. Lindlar, mild reduction. Normal, without this barium sulfate and quinoline, it is going through complete reduction. Okay, then when these are having this terminal hydrogen, see when you're having terminal hydrogen, this terminal carbon, hybridization is sp, s character high, electron negativity high. This carbon has some sort of acidity, so this can take up these electrons, leaving this hydrogen away. Some sort of acidity. Now you guys done equilibrium. pKa greater mean acidity is high. Since it's acidic, it is showing some other reactions as well. Acid plus metal, salt and H2, that reaction you guys know. Same as sodium, sodium iodide is reacting to give this sodium acetylide. See, this is your very first chain extension reaction with sodium or with sodium. Once you make the sodium acetylide, that with alkyl halide, you are going through chain extension, your very first chain extension. Now you have 5 different chain extensions. See how your organic life is easier with my short notes, same as inorganic chemistry, but we are practicing in a different way, not the way we did inorganic chemistry. With the Grignard, also Grignard accept these H pluses. And this R and H getting away as alkanes, then the rest of the part is joining to this Grignard. This is the main part that we need, not this alkanes. Then these two, 4 and 5, ammonical cuprous chloride, ammonical silver nitrate, both these are identification tests. With these two, they are making covalent bonds with copper and silver. Copper, red, brown, silver, white precipitate. Formation of alkyne. To make 2 pi bonding, you're supposed to have either 2 halogens or 2 hydroxyl. You guys know what are these reagents to add. Then formation of C2H2 I've given because it's not in unit 14 now. See, now you can go with third box. Then again, I want you guys to go with the first, second, third box together. Then try to do these questions. Now you would see when you are doing these questions, it would take less than half an hour, maybe 20 minutes or so doing these 12 questions. But if you remember, we did this question during the class time. I took more than 4 hours. One single day, we did only these 12 questions. If you remember that. Those 12 questions we did at the class. Then I've given another 12 questions for your practice to do at home. That's how you started your conversion life. Moving to benzene. Okay. They found out benzene made up of carbon and hydrogen. And its molecular formula is 78. Then they could find this, molar mass is 78, so that they could find this molecular formula. Then they went through these structures, considering that they are supposed to be unsaturation. But then they will find out these compounds who's reacting with unsaturation do not react with benzene. Then they came with this single bonded structure again. Later then they found out, even if they are not reacting with other chemicals, they are reacting with 3 hydrogens. So they are supposed to be some sort of unsaturation. Then they ended up here. But then they identified again, if you have that structure, if you have this structure, they are supposed to be 2 different structures when you're adding 2 halogen. But then they found out there are no two different structures. They have only one single structure, even if they were adding two halogens. Then they came across with these two theories, resonance theory and molecular orbital theory. These two structures are just interchanging very fast, so that it is existing as a resonance hybrid. You have just one single structure. That is the resonance stability. Okay, so if you have one single in double bond to add one hydrogen, releasing 120. For three hydrogen, it's supposed to be 360. But when they were done that with benzene, it was 208. So 360 minus 208, that much amount of stability already can be seen in benzene. That is called the resonance stability. Okay, again, we can show it using this energy level diagram and this orbital diagram. So that benzene is having this, this is the structure of benzene, planar, cyclic, continuous, and delocalized electron cloud. Okay, this is the other part. These general naming, just add to one single place and memorize them. I mean, almost all these you guys know now. Physical properties just go on easily. Benzene reactions, how the electron density is really high, and you have three double bonds. You can break them, but you cannot break them because it has this resonance stability. Anyway, since the electron density is high, electrophiles are coming. So benzene is little tricky, cuppity. So what does he do? Like a beggar comes requesting something. He's really rich, but he's not giving that away. So he's just giving away one of these hydrogens and joining back another there. So it is going with electrophilic substitution reaction. Addition and oxidation possible, but with extreme conditions. So the nitration, addition of NO2, but here nitric, sulfuric, and 50 degrees Celsius. You're supposed to use this sulfuric catalyst and also temperature a little higher for the reaction. Anyway, what happened here is, according to Lowry-Bronsted theory, H2SO4 is stronger compared to nitric. So that H2SO4 given H plus away acting as acid. It is taking in nitric acting as base. Then it is protonated by this oxygen and it's breaking from here, making NO2. That NO2 is attacking onto the benzene and joining there, going through the resonance structure. It is making this nitrobenzene. I know you may have forgotten these mechanisms and everything. Just draw once. And I asked you guys to make these mechanism. I didn't give you guys this mechanism short note. I mean, I asked you guys to draw that. So whenever you are drawing each of these, just do it in one single paper, then add them together. While studying, you can make the set. So you're not spending separate time for add all the mechanisms together. Action of H2SO4, it is acting as a catalyst and gives the protons acting at dehydration and re-establish the aromaticity, so a lot of stuff there. Then halogenation, here again you need this catalyst, and here the chlorine is acting as lone pair donor. So that's the electrophile. C plus is an electrophile. So once you come here, this C plus is really unstable. So it is dragging electrons from this direction. So this chlorine, it is not joining here with this bulkiness, space inability. So this chlorine is joining here onto benzene. And then going through the resonance stability, you are making chlorobenzene. I guess okay so far. Be really alert so you don't have to read, listen this again once you go home. If you are really alert. Okay, then Friedel-Crafts alkylation and acylation, you are joining R groups, but only one single R group without any other substituents that you can go with the Friedel-Crafts alkylation. Again, the same reaction, that this chlorine donating its lone pair onto this electron deficient aluminium. So you are coming to this intermediate. Again, this is dragging electrons away. R gets plus. So this is joining onto this benzene ring. So going through these resonance structures, you are making this alkyl benzene. You have a little problem here. How do you know that R can join separately or together? If R is stable, it is come separately like this. tertiary carbocation is stable. Allyl, benzene carbocations are stable. They can join separately. See, it is joined separately with benzene, but methyl carbocation, primary carbocation are unstable. So when it is attacking onto benzene, the full complex is coming and attacking to benzene. Memorize that. Then Friedel-Crafts acylation, CORO. If you go to the mechanism, here the important thing is that same complex it is making, but that complex is existing this way separately because RCO is again stable. That's because it can go with this resonance stability. See, RCO joins separately. That is the only difference between alkylation and acylation. I'm just giving you these highlights and emphasizing things that to make it easier to go on with the theory note. There are two addition reactions. You need extreme condition. One condition is not only hydrogen nickel, but we are making this nickel some sort of a special way, special powdered nickel that we call is a Renai nickel to get this cyclohexane or hexabromocyclohexane by Br2H new. Oxidation is again little trickier. They are not oxidizing. They get oxidized, only the groups on that. Benzene does not go through oxidation. Any of these strong oxidizing agents we can use. CCRO3 strong oxidizing agents. Okay, any of these groups, whenever there is a CH, even a one CH is supposed to be here, can oxidize to one single COOH. But this doesn't have any CH. So tertiary carbocation cannot oxidize by these potassium permanganate, so any of these strong oxidizing agents. Formation, disonium H3PO2 or aryl halides converted to Grignard, add water, go back to, okay, now you're going to go to this benzene box. Okay, it's again really important when the second group is coming onto benzene, another electrophilic substitution, second group. So that controls by the first group already joined, rate and the orientation. First let's consider the rate. How it control the rate of the second group who's coming. Let's say first group is a ring activator. So this provides electron onto this ring. The electrophile needs more and more electron. So that when the ring activity is more stronger, more electron density inside the benzene ring, second electrophile can come and join Anu faster. Okay. Then the ring deactivator. They deactivate means they drag electrons away from the benzene ring. So that second E plus is now discouraging. So that less speed. Okay. So the ring activator and ring deactivator. I'm not explaining this table because I've given this increasing order of this electrophilic substitution. Then we are going to which position they can join. There are three different positions, but we categorize them into two different positions. This is ortho and this is para. So to ortho position or para position, one single group, and then these two are meta. Meta is another position. If they activate ortho and para, this second group is going to ortho and para. If they deactivate ortho and para, less electron density in ortho and para, then they are going to meta. Is that clear? They are not activating meta. They are deactivating orthopara. So it is going to meta. And here again, all ring activators and weak ring deactivators are orthopara. Strong and mild ring deactivators are meta. Do you guys believe me? Even for your term test, I guess you already done that. And for your final exam, you would read these notes even faster that I'm explaining here because your memory is then totally completed. All right, done with that part and couple of conversions we did. Done. Yeah. Okay. Hydrocarbons, halohydrocarbons, 5 different groups. Haloalkanes, halogen directly join into carbon. Haloalkene, halogen joining to double bond, vinyl and allyl. Haloalkynes, halogen directly join into triple bonded carbon. Haloarenes, halogen joined to benzene carbon, benzyl halides, halogen joined to a carbon, that carbon joined to benzene ring. They are polar compounds, so they have dipole-dipole interactions. So halogen gets away, another group joins, nucleophilic substitution, then explaining couple of these compounds are not participating for nucleophilic substitution, SN reaction. Y9 halides are not participating. See, one thing is this carbon sp2 more electronegative. It doesn't like to give its electrons away. And when these lone pairs are delocalizing this CX1, CX1 gets a double bond nature, so hard to break it. So Y9 halides does not participate for nucleophilic substitution, but with the same two reasons, alyl halides. See the hybridization is sp3, less electron negative. And once you make that plus charge, it can delocalize it in the ring. So the resonance stability. So alyl participate, SN. Aryl again, same two reason, but not participating. One thing is electronegativity is high, gets sp2. The second thing, when they are providing electrons and delocalizing within the ring, CX, double bond nature, so you cannot break. So alyl halides do not participate for nucleophilic substitution reactions. So the benzyl halides, see the sp3, less electronegativity. Once you remove this halogen, so you are getting this carbocation, delocalizing within the ring, it's now getting stable. So benzyl halides are very easy to participate for SN reaction. See, now we're done with kinetics. SN1 or SN2. It depends totally on this carbocation stability. If the carbocation is stable, it can exist in the medium separately. This reaction occurs separately, making the carbocation. Then joining the carbocation with the nucleophile, this reaction again happens separately. You have positive and negative, so this reaction is faster. Here you are breaking this one, so this is slower. Only this is controlling the reaction rate, so it is SN1 first order reaction. But in this kind of a situation, let's say that you have just a CH3 group. That's unstable. It is not existing in the medium as it is. Methyl carbocation unstable. So breaking this, joining nucleophile happens at the same time. So that both supposed to react the reaction. Both supposed to control the reaction rate. So that is second order. So aqueous sodium hydroxide halogen gets away OH joins to make alcohols. Alkoxide ion ether. With ammonia, they can make primary amine, secondary, tertiary, and quaternary ammonium salts. Acid-light ion, remember earlier we said that acid-light reacts with alkyl halide. Now we say alkyl halide reacts with acid-light, same reaction, chain extension. Cyanide reaction, again, halogen gets away, cyanide joins. That cyanide with acid, COOH. That cyanide with lithium aluminum hydride, CH2NH2. Elimination reactions are also possible. That is a beta elimination. When the medium is having OH minus, it is attacking onto beta hydrogen. And then this one polarizes to this direction, making a double bond. So halogen again gets away. So that's elimination. Okay, Markovnikov, when you are joining hydrogen, hydrogen joins to where hydrogen is high. Say it's F. When hydrogen gets away from the carbon where hydrogen is less. Say that. Okay. With metals, they are making Grignard. To make Grignard, you need magnesium and dry ether. So this magnesium, it is making two covalent bonding here. But still, these two are electron negative comparing to magnesium. So both these are trying to drag electrons from its direction. That's why Grignard is really unstable. So in this polar, non-polar medium, these oxygens are donating electrons to control the electron density of this magnesium. So in the presence of any of these compounds, that's why Grignard is inactive. So we are going with the reactions of Grignard. So the main reaction is proton donors. Grignard can take some H plus from any H plus given compound and convert into alkanes. Only difference is here. With carbon dioxide and with water, it is making carboxylic acid. Memorize that. All the other are normal reactions. Carboxylic with carbonate compound, it is joining one R group. Aldehydes and ketones, primary, secondary, tertiary, so on. Then I'm going with ester and acid halide together. Esters and acid halides together, they connect two identical R groups. Formation of alkyl halides, you can have double bonds with HX, maybe Markovnikov or anti-Markovnikov, and also ROH, PCl3, PCl5, Cl, PBr3, OH convert into halogen. See, we done all this. How lucky you guys are. Other classes are still doing this organic. Can you believe that? I'm so sorry about that. Okay, oxygen containing compounds, alcohols, hydrogen bonds, just go with that. Moving on to chemical reaction, C10. Acidity, they have some sort of acidity, but less acidic compared to water because inductive effect, decreased acidity. Go through the note if you are not still comfortable. So that highest acidity goes with the primary alcohol, tertiary least acidic. Why they are acidic? Because they react with sodium to release H2 gas. They are not reacting with sodium hydroxide. Some sort of a basicity is there, they react with more acidic compound, they get H pluses from more acidic compounds. With carboxylic acids, they are making esters, and with acid halides, they are making esters. But acid halides are stronger, so you don't want this kind of external driving force like 80 degrees Celsius or heating, but you need that with carboxylic acid. With Grignard, this H plus can, again, the annotation went away. Alcohol H plus can donate onto Grignard, so it is making this again this alkane compound, so saturated alkanes reacting Grignard with alcohols, alcohol H plus. Lucas reagent, same reaction that they are making alkyl halides, but the difference here is we are using this catalyst, so the reaction is really faster. So for tertiary, since going through the tertiary carbocation, it's stable, instant turbidity, 10 minutes and after 1 day. So we are using them as identification test. So the next one is with HBr, this OH, lone pairs are donating, this bond breaks, water molecule gets away, bromine joins and converting to alkyl halides. Phosphorus halide, same reaction, converting alkyl halides, but the byproducts are different. Oxidation, strong oxidizing agents, depending on primary, secondary, tertiary cannot oxidize. They can make either carboxylic acids or ketone. Mild oxidation, remember that if CrO3 separately in the medium, that is a strong oxidizing agent. But this time we are adding pyridine. With pyridine, it is controlling the oxidation strength. So they just only go up to aldehydes. Ketone are same. Tertiary are not oxidizing, even strong or medium, mild. Dehydration we did earlier, the way we are getting these double bonds. That's again going through the 8 steps rule. How many questions? Do you guys need this many questions? Okay, so the next part is the phenol. It is not alcohol. Another part of compounds, phenol, OH hydrogen bonds, but water insoluble with this water repelling property of benzene ring. Some sort of acid is there. So it is again giving these H pluses to the medium, but still reversible because the acidity is weaker. This is where acidity is greater comparing to alcohol, because here the negative charge can delocalize within the ring. It's more stable, so that not like alcohols. Alcohols react only with sodium. Phenol can react both with sodium and sodium hydroxide. And acidity controls by these groups joining. When ring activator joining, less acidic. When ring deactivator joining, it is dragging electrons away, so that H plus can get easier, so that's more acidic. Acetophisomers, we're just going to talk about this one. So this OH group is activating ortho and para. So when another deactivator join into ortho and para, it's very easy to drag electrons away. So when it is closer, dragging is more efficient. But the thing here is, even it's closer, they are making hydrogen bonds. That's why para greater than ortho, but meta is not activating, so meta is less. Esterification can go for phenols only with acid halides. There are no substitution reaction. One is S character high, more electronegative, and the second is through the resonance they are making this double bond nature on this onto this CO. So you cannot make these bonds. You cannot break these bonds. So there are no SN reactions in phenol, but they are showing this electrophilic substitution same as benzene. But still, OH is really active. So you don't want extreme condition. No catalyst, just the benzene. And still, see, all these 3 points are activated. So 3 benzene are joining, bromine are joining to make this white precipitate. And nitration is also possible. See, the nitration mixture is now very mild, diluted, and less temperature. Formation of dye. With respect to benzene, it is electrophilic substitution. This hydrogen gets away with this chlorine. This nitrogen is joining with here, and this is that one. They are making this orange color dyes. Complexes that memorize again, same as the salicylic ferric reaction, they also can make purple color complex with ferric. That is an identification. Formation of phenol, we can directly come from sodium nitride with HCl. NH2 is converting to OH, or with low temperature, NH2 is making disonium, then addition of water and heating gives back this phenol. You can go through that path as well. I guess okay. I guess okay. Yeah, we can do this. Moving on to carbonyl compounds. CO group is there for carbonyl compounds. They can make hydrogen bonds with water, water solubility, polarity, melting boiling points, just physical stuff you can just go on easily. So the reaction type, you have this carbon here. To that carbon, oxygen is joining other 2 groups. So this carbon gets delta plus, this is delta minus, because this always these bonds are polarizing towards this oxygen. So this is delta plus. Who's come and joining? Nucleophiles. What do? They break the bond. So the characteristic reaction type is nucleophilic addition, breaking bonds, addition. These are the different reactions. So first one go with, see the reaction rate increases, less inductive effect. More inductive effect means C plus is weakening. So nucleophiles are discouraging. Okay, with HCN dissociate into H plus and Cn minus. That H plus, that Cn minus directly attacking onto this CO and joining. Then another HCN gives this hydrogen to this oxygen to make this cyanohydrin compounds. Once you make that Cn, wherever Cn, with lithium aluminum hydride, CH2NH2, same Cn with acid convert into COOH, that is oxidation. With Brainerd, they are joining 1R group to make these alcohols. And again, nucleophilic substitution reaction. So this R is now negative. See the delta minus. Joining here, nucleophile, break the double bond, nucleophilic addition. So nucleophilic addition. So they are joining 1R group. With Brady, see, today we talked about this Brady. This is a 2,4-DNP or Brady. 2,4 dinitro phenyl pyrazine. Okay, what happened here is they are making these dyes. Initially, this lone pair on this nitrogen attacking onto this CO group. CO bond breaks. So it's again a nucleophilic addition reaction. But once you are coming here, this nitrogen is now unstable with this plus charge. This CN bond, sorry, HN bond, polarizing towards nitrogen, and this is getting away. So then you are coming to here, but still see, this is electronegative, this is electronegative, and this is electronegative, so it's unstable. So it's rearranging. This NH bond breaks and make the double bond here. so that this bond also getting away. So making a water molecule. Making this double bond, we call these compounds imines, but this is a orange color precipitate. Aldol condensation is the hardest. I'm not going to explain everything now. I have rewritten the aldol condensation for make it more easier for you. Anyway, for that you guys needed this alpha hydrogen. This is your carbonyl. The adjacent carbon is alpha carbon. So this one has this one too. And then the alpha carbon join into alpha hydrogen. If you have hydrogen here, those are also alpha hydrogen. So if you have alpha hydrogen, those hydrogens are acidic. So they are going through nucleophilic substitution reactions, nucleophilic addition reactions. How do you make this nucleophile? Nucleophile itself is again another carbonyl compound. When this OH is attacking onto this hydrogen gives its electron onto this carbon and gets away. See, this carbon gets a plus charge. And with ketoenol, this transition, this compound is also stable, and this is also acting as the nucleophile. And that this is how they made nucleophile. So this nucleophile here is attacking onto this carbon. This one polarizing towards this direction, so nucleophilic addition. Then this oxygen gets a hydrogen here. So I have written this part this way. That is the only difference. If still here this is harder, just go through very nicely slowly. Only thing is, same two molecules are reacting together. That's why if you feel harder, that aldol is harder. With acid light ion, whether it's sodium acid light or acetylenic grignard, it is reacting to give this alcohols but connected to triple bonds. Remember that. Metal hydrides, lithium aluminum hydride and sodium borohydride, that you have to memorize. This lithium hydride hydrogen is joined into carbonyl carbon. Water hydrogen is joined into carbonyl oxygen. Clemmensen reduction, you guys know, making alkanes. Oxidation, only aldehydes can oxidize to carboxylic acids. Mild oxidation with tolerance and failings, those are identification tests. With tolerance, they are giving this Sidler mirror, and with failings, they are giving this, even failings we talk about under inorganic, they are giving this brick red color. Then formation of aldehydes, few methods, but you can go with this only one of these alkynes, alkyne hydration aldehyde, or PCC with any primary alcohol aldehyde. Ketones are making easier. This secondary, any of these secondary alcohols oxidize to give ketone, and this is Friedel-Crafts acylation, and also this triple bond, whatever the triple bond, hydration gives the ketones. Come on. Okay, carboxylic acids, COOH, hydrogen bonds, that part. Then the first reaction is acidity. These are the strongest acids in organic chemistry. So that they react not only with sodium and sodium hydroxide, carboxylic acids also reacts with sodium carbonate and sodium bicarbonate as well. Okay, when ring electron attracting groups are joining, acidity high. When electron attracting group, the group which is more electronegative, joining closer to COOH, acidity high. When the electronegativity is high, acidity high. And inductive effect less, acidity high. And ring activator, acidity less. Ring deactivator, acidity high. Listen twice this, then you would feel really comfortable. I'm just reading your note. I'm not reading something that we haven't done. Basicity. It can take up H pluses from more acidic compounds. With alcohols, they are making esters, we did earlier. With ammonia, they are making amides. With phosphorus acid, they are making acid halides. Reduction only go with lithium aluminum hydride to make these alcohols. But special reactions are there for formic acid. All the other reactions are these redox reactions. Formic acid is oxidizing from +2 to +4. Only different reaction is this dehydration reaction. Here, oxidation number is not changing. Then there are, just go through this, you can understand. More time. Then there are three derivatives. Out of these three derivatives, I'm first going to go with the acid halides. Acid halides are COX. These are really, really reactive even compared to carboxylic acids. Acid halides, amides, and esters. Particular two characteristic reaction types: nucleophilic substitution and reduction. And here, halogen gets away, OH joins with when addition of water. With sodium hydroxide. First part is OH minus attacking onto this carbon, double bond breaks. So the reaction type is nucleophilic addition. If you get this little part separately, here you can see only halogen is getting away. Only halogen is getting away. That is elimination. But finally, if you see this X is getting away, this ONA joining. So the reaction type finally becomes nucleophilic substitution. These with alcohols or phenols going through the esterification. For alcohols, they need, they don't want any of this external support for that. With Brina, they are joining two identical R groups. With ammonia, acid halides are also making amides. And with primary amines, they can also make this substituted amides. Reduction is possible with both lithium aluminum hydride and sodium borohydride. They are making these primary amines. Then moving to esters. Ester reactions, they very easily. So the first type is the nucleophilic substitution. See, this part is getting away as nucleophile and joins OH. So that's a substitution, but this is a hydrolysis of ester. With sodium hydroxide basic medium, instead of COOH, now it is converted to COONA. Greenard, two identical R groups. Reduction can only reduce with lithium aluminum hydride to give the mixture of alcohols. Amides, RCONH2, they have hydrogen bonding. Basicity is there, but basicity is less because when they are making these resonance structures, see this has a plus charge. So these are less basic. With sodium hydroxide, sodium salt of carboxylic acid, wherever you have sodium nitride LHCl, NH2 is converted into OH, converted into carboxylic acid. Only one single reaction, that is dehydration. With P2O5, they are making nitrides. Reduction, only with lithium aluminum hydride, they can reduce. Amides can reduce to primary amines. Finish. There's more to go. Okay, last unit, that is the nitrogen containing. That's again very easy. I'm going to go to these chemical reactions. So we're going to talk about their basicity. These are the highest basicity, but basicity is greater even basicity of alcohols, because alcohol has this oxygen, less basic, and plus charge, less stable. Even you have plus charge here, less electronegative, and donation of this lone pair is then easier on amine comparing to alcohols. Aniline less basic compared to amine because the lone pair is delocalizing within the benzene ring. When you have ring activated, basicity high, ring deactivated, basicity is less. Little more to go. And also, out of these three, highest electron density goes to tertiary. But best basicity is going with this secondary, because here we have the steric effect in tertiary one. The molecule cannot get closer to that. Then when you are going with reactions, alkene halides again going with primary, secondary, tertiary, and quaternary ammonium salts. With nitrous acid, I'm going these two together. Aliphatic and aromatic. Aliphatic, diazonium unstable, does not exist. But aromatic diazonium stable. So this is spontaneously converting to ROH. But here we have to add water and heating to convert this into phenol. Acid halides, they are making this substituted amides. With carbonyl compounds, they are making imines. Bromine water, same as phenol, they are making white precipitation. Formation, you can just go on. Aniline, that's easy. One single page we have. Diazonium salts, you have this aliphatic and aromatic diazonium salts. Anup, concentrate, little more to go. Aliphatic, but here through the inductive effect, they try to stabilize this nitrogen, but that's harder. But here can delocalize within the ring. So more stability in aromatic. That's why aliphatic unstable, aromatic is stable. One reaction is the displacement. N2Cl gets away and N2Cl is displaced by OH by addition of hot water. Or the next one with H3PO4, N2Cl gets away, make benzene. Potassium iodide, N2Cl convert into iodine. This Sandmay reaction, this person, he made these reactions with catalyst. So they can make this chloro, bromo and cyanobenzene. Last page, last little thingy, making dye. Two different reactions we did with phenol and beta naphthol. Phenol, they are giving orange color precipitate. Beta naphthol, red color. This is the beta OH. This chlorine joins onto this hydrogen. And this is again electrophilic substitution. This hydrogen gets away with this chlorine. Okay. Done with all these four. This is beautiful. Okay. I know I went a little faster, but do you guys feel like you didn't know this? When I was reading this, you were feeling like, wow, we read about this. Maybe I remember this part. I have forgotten this part. So what are you supposed to do? I want you guys to go home today, and today itself, if it's possible, go through all these short note stuff and spider diagrams. Then you can memorize that. If it is possible, the same way we took like 1 hour to go through the full note. If you can just turn pages and get a little idea, then next time when you are being relaxed and when you study the note, you have a good memory. Go like that. That's why I did this part. Understood? All right, let's stop there. Bye, take care, everybody. Next week, next week no class. I'm sending anyway this recording.